Okay, let's start our new chapter, amplitude modulation. Okay, so in the first chapter, introduction, you were introduced to the term modulation. Yeah, I've mentioned modulation few times, and also I highlighted the importance of modulation. Yeah, so especially because we need to make sure that the signal that we want to send is suitable with our medium. Okay, so what is modulation? So our information is can be audio, text, video, etc. So modulation is the signal transformation to a format suitable for transmission through a chosen medium. So the signal actually transforms in terms of, especially in terms of its frequency change. Yeah, because like I said, the medium's frequency is normally higher than our information signal frequency. So apart from signal, another important signal that is involved in modulation is our carrier signal. Okay, so our message signal, which is our modulating signal, will modulate the carrier. Yeah, it modulates the carrier, and then this will result in the modulated signal. Yeah, and then this modulated signal will be shifted to a higher frequency. Okay. So in general, there are two modulation types. First is the continuous wave modulation, and then secondly is the pulse modulation. Okay, the continuous wave modulation. So this is when our carrier is a sinusoid signal, analog signal, a sine which is an analog signal, and this is also the this is also the main modulation type for all analog communications, especially for AM, FM signal. And pulse modulation is when our carrier is not sine, but it's a pulse string. Yeah, you can imagine it's like a series of square waves. So in this case, our produced modulated signal will be also in pulses 1s and 0, and this is for digital modulation. Yeah. Okay. So this is my first day working from home after our last PKP. So if you can hear any noises like children chatting, talking, please inform me. Okay. Okay. So why do we need modulation? What are the benefits of modulation? Okay, so modulation shift the spectral content of a message into a band which is better suited for our medium. So like for example, in wireless, in wireless we're using antennas to receive the signal, and this transmission and reception of signals only happen at certain frequencies. Okay, so the design of our antenna, which is our the size of our antenna, will depend on the parameter wavelength. Okay, and this wavelength, of course, is related to frequency. Okay, so if we use because of the inverse relationship between lambda wavelength and frequency, which is okay, lambda is inverse to our frequency. If our lambda is larger than f is shorter and vice versa. So if we want to have a very compact mobile phone with small antenna, we need to make sure that the frequency should be high enough. So that is one of the importance of modulation, shifting our spectral content to a frequency that is suitable for our channel. All right, another benefit is that it allows the use of multiplexing. Okay, so by having this multiplexing, we can utilize our capacity, our medium capacity better. So we can have simultaneous communication by many users on the same channel. Okay, for example, if you look at the FM radio broadcast, so the FM radio station basically broadcasts audio signal, which can be up to 4 megahertz, for example. So regardless of which radio station, the frequency range or the bandwidth will be of our signal will be about the same. So, but at your radio, you can tune to many frequencies, right? So instead of having only one radio station transmitting their signal, we can have many radio stations. We can have many radio stations, transmitting the same audio range. We just give different frequency to these radio stations. Radio station 1, for example, 88.0 megahertz. Radio station 2, 88.1 megahertz. Okay, so by having this, we can have many radio stations using the same medium, which is air. And some modulation techniques also have superiority, advantages in some aspects, like frequency modulation, for example. It has superior performance over noise or interference. Okay, so that's the overall information on modulation, general information on modulation. So we look at the first modulation type that we will learn in our course, which is amplitude modulation. Okay, so the objective for this chapter is to learn about AM modulation and demodulation techniques, and to learn about the AM generation and detection. Okay, so there are a number of AM variants that we will learn. Okay, so the first is double sideband full carrier. Second, double sideband suppressed carrier. And then single sideband with carrier, single sideband suppressed carrier, and vestigial sideband. Okay. Okay. So this is still kind of general information. So differences between baseband and carrier communication. Okay, so for baseband communication, this is the one that do not involve frequency shift, but this is not practical for our commercial world. So because it uses a very wide frequency range, and it's also applicable only for wired, or cable transmission. But the most common is using carrier communication, where we use modulation. Shift the frequency. Okay, sorry for the disruption. Okay, so this is one of the challenges for lecturers when we work from home. Okay. Okay, so let me continue. So for carrier communication, we use modulation technique. Yeah, and then this modulation will change the carrier signal's characteristics. Okay, so for carrier communication, so it's suitable even for wireless. So for wireless, we must use modulation. Okay, so just in my previous slide, I mentioned that a number of carrier signal characteristics that we can change to modulate. So let's use this illustration. So from you have learned this in previous courses. So this is basic information about signal. Okay, imagine VCT is our carrier signal and VMT is our modulating signal. So for VCT, any signal can be represented using this general equation. Yeah, A is the amplitude, and then we have cosine omega ct plus phi, where omega c of our radiant frequency is our phase, and it's actually the one attached to cosine is actually our angle. Okay, so exponential form is also can be represented using exponential form, amplitude and angle, where angle is actually made up of frequency and phase. Okay, so these are the carrier characteristics that we can change to follow our information signal. Okay. In other words, our information signal will change at least one of these characteristics, either amplitude, frequency, or phase. Or for advanced modulation techniques, they can also use combination of these characteristics. Okay, so let's look at the first variant, which is the double sideband full carrier. So for double sideband full carrier, or known as full AM, so this is the most conventional, most fundamental modulation process. So the carrier frequency signal is much higher than our modulating frequency signal. And we have our AM modulator. Okay, our AM modulator, we have two inputs, the VMT modulating signal and the VCT carrier signal. Okay, so and the output from our full AM signal can be represented by this equation, okay, which is equal to EC plus VMT cos omega CT. So this is the general equation for full AM. Okay, so let's make further analysis to understand about this. We want to look at the spectral component of this full AM, and also bandwidth, power performances. Okay, so our VMT is equal to EM cos omega MT, and VCT equal to EC cos omega CT. So VMT is our information signal, and VCT is our carrier signal. EM is our amplitude, VMT signal's amplitude, EC carrier's amplitude. Okay, so VAMT is equal to EC plus VFT times cos omega CT. What's that? Okay. So if we substitute VMT equal to EM cos omega MT, then becomes EC plus EM cos omega MT cos omega CT. Okay. And for full AM, this is only for full AM, the modulation index is equal to EM over EC. Okay, which is the information signals amplitude divided by carrier signals amplitude. So this is the definition of modulation index for full AM. Okay, and then if you take the EC factorized outside, we can have this EM this over EC for the cos omega MT term, and then this can be represented by using M. So it becomes EC in bracket 1 plus M cos omega MT times cos omega CT. Okay, and using identity, trigonometry identity, cos A cos B equal to half cos A plus B plus half cos A minus B. Okay, we can expand this equation above here. So it becomes EC cos omega T plus M EC over 2 times cos omega C plus omega MT plus M EC over 2 times cos omega C minus omega MT. Okay, so this you can see from here, and there are 3 spectral components. So we have 3 terms at frequency of omega C plus, omega M, and omega C minus omega M. Okay. Is it okay so far? Any problem? Okay. So let's continue if there's no problem. So from the spectrum, from the equation, we can see the EC cos omega CT is our carrier signal, and the other two are known as the sideband signals. Okay, so the sideband signals, the frequency is omega C plus omega M and omega C minus omega M. So if it's lower sideband, it's omega C minus omega M. If it's upper sideband, is omega C plus omega M. Okay, and the amplitude of our new sideband signal is MEC over 2. Okay, so it's the same amplitude for both lower sideband and upper sideband. So MEC over 2 is also equal to EM over 2. So what does this mean? What does it mean? So before modulation, okay, so this is just to illustrate. So before modulation, our information signal at omega M here, the amplitude is EM. Okay, and then we have also our omega C, carrier's frequency at EC. Okay, so before modulation, we only have this EM, omega C and omega M. And after modulation, we have new components, the LSB and USB. And what happens is that the upper sideband and lower sideband's amplitude will be half. So the EM will become half. Okay. So that is the spectrum. So this is known as spectrum. Sorry, this one. This is known as spectrum. So it's amplitude versus frequency. And this is waveform. Waveform is the amplitude versus time. Okay. So M is equal to EM over EC. And there are three scenarios. So the choices of our M will affect our signal's performance. And there are three different scenarios. Okay, when M is equal to 1 or EM equal to EC, so this is 100% modulation. Okay, so this is how the waveform looks like. When M is smaller than 1 or EM less than EC, then this is how it looks like, the waveform. And M larger than 1, which is EM larger than EC, this is over modulation. This is how it looks like. Okay, so the last condition is known as overmodulation. Okay, for overmodulation, this is something that we do not want, because it will cause loss of data. Because normally we use envelope detector to detect our full AM signal, and then this envelope detector will take only one of the cycles, whether positive or negative cycles. If you notice here, actually this dot here is our information, represents our original information signals, VMT. And it's the same. It's actually it's mirror between positive and negative. Okay, so at the detection, it will take one of the cycles, like positive cycles, and then we'll detect the envelope of our AM signal. So if the positive and negative are mixed, then if the envelope takes only the positive, then it won't represent the original information signal. Okay. Okay, any problems so far?
Doctor, I didn't understand the sideband effect in the modulation.
The side effect of overmodulation?
The sideband effect of the modulation. Like, I didn't get the concept of it.
Of which one? Sideband?
Yeah, the sideband, the lower and the upper one.
This one?
Yes.
Upper and lower sideband?
Yep.
Okay, it's like this. Our information signal before modulation, sorry. Okay, we have our VMT and carrier, right? These are the two inputs of our AM, and then this is the our VAMT, the AM modulated signal. So if you, and then we perform analysis, we perform analysis to look at the spectral component. When we multiply modulating signal and carrier signal, what happens? So what happens is that instead of two original signals, VMT and VCT, we have the original we have two, now we have three. The carrier, and then there's no more VMT. What we have is the upper and lower sideband. So these are the three signals that are produced as a result of our AM process. Okay, is it okay?
Okay, understood.
All right, good.
Doctor, yeah? one more question regarding this thing. Earlier you mentioned modulation. Okay, I think I rephrased the question. How does upper sideband and the lower sideband relates to the purpose of modulation. I can't see the connection between what is going on and how does this translates to what modulation is doing.
Okay, thank you. So, like I said, first our VMT, our information is carried by our information frequency, which is low frequency. So we modulate, we want to increase its frequency. Okay, so when we modulate, increase its frequency, the result is this. Yeah, the upper and lower sidebands. The upper and lower sidebands have higher frequencies, much higher than our FM. So this helps in the modulation process itself. And then this is in spectral, in the spectral component. And if you look at the waveform, okay, so this waveform of AM signal, it consists of FC, FC plus, and FC minus FM. Okay, so these are higher frequencies. But this waveform of higher frequencies also carries the low modulating signal frequency at its envelope. Okay, so it helps in having shifting from low to high frequency. Okay, so I hope this answers your question.
Okay, thank you, Doctor.
Then we look at more analysis on the waveforms itself. Yeah. Okay. So this is our waveform. Yeah. Our the frequencies inside here are high frequencies. Yeah. That is actually a combination of FC, FC plus, and FC minus FMs. If you look at the dotted lines here, if we trace the peak of our amplitudes here, because the amplitudes are changing here, right? If we trace the peaks, peak voltages here, yeah, the dots, this actually is our VMT. But our VMT is shifted by EC, okay, because originally should be at 0, centered around 0, and then it's shifted by EC. So the dotted here is known as the envelope equation. So it's EC plus VMT. So we have our information signals at the envelope of our modulated signal. Okay. So it has positive and negative cycles. So basically they carry the same information. It's just the mirror image. For example, here it's above positive envelope, below negative envelope. Okay. And if you look, we can actually calculate our modulation index from the information or the parameters on this related to the waveforms. Okay, so V between this is known as Vmax positive up here, Vmax positive. Below here, the most negative point is Vmax negative. Okay, so here is Vmin positive, and on negative part is Vmin negative. So M can be found as Vmax positive minus Vmin positive divided by Vmax positive plus Vmin positive. Or we can also use the minus cycles, the negative cycles. There are a number of ways to calculate M using Vmax peak to peak, Vmin peak to peak. So Vmax peak to peak is difference between Vmax positive and